Installing a variable frequency drive, commonly known as a VFD, on a common well that also supplies power to adjacent homes can potentially create harmonics issues. These high-frequency harmonics generated by the VFD can cause several problems for nearby homes. One potential issue is nuisance tripping of circuit breakers. The harmonic currents can interfere with the operation of circuit breakers, causing them to trip unexpectedly, disrupting power to the homes. Another issue is flickering or dimming of lights. Harmonics can distort the voltage waveform, leading to fluctuations in light intensity. Thirdly, there is the risk of damage to sensitive electronic equipment. Harmonics can cause overheating, malfunction, or premature failure of electronic devices. The open Y-open delta configuration of the transformer can exacerbate the harmonics issue. This configuration provides a path for harmonic currents to flow through the neutral conductor, potentially increasing harmonic distortion on the line. To mitigate potential harmonics issues, several measures can be considered. Firstly, use a VFD with low harmonic distortion. When selecting a VFD, choose one with a low total harmonic distortion (THD) rating. This will minimize the amount of harmonics generated by the drive. Secondly, install a line reactor. A line reactor is an inductive device that can help to absorb harmonic currents and reduce THD. It is typically installed on the input side of the VFD. Thirdly, use a harmonic filter. A harmonic filter is a device that is designed to trap and dissipate harmonic currents. It is typically installed on the VFD output. Fourthly, upgrade the transformer. If the existing transformer is not rated for harmonic currents, it may need to be replaced with a transformer with a higher kilovolt ampere kV rating and improved harmonic performance. Fifthly, consider isolating the well power supply from the power supply to the adjacent homes. This can prevent harmonics from flowing into the homes. To assess the potential impact and determine the appropriate mitigation measures, it is recommended to consult with an experienced electrical engineer. They can conduct a harmonic analysis and recommend the most effective solution. A harmonic analysis will measure the existing harmonic levels in the system and predict the impact of the VFD. The electrical engineer can then recommend the appropriate mitigation measures to reduce the harmonic distortion to acceptable levels. When choosing a VFD, it is important to select one that is designed to minimize harmonic distortion. Look for VFD with built-in harmonic filters or those that use advanced control techniques to reduce harmonics. Installing a line reactor or direct current DC choke can also help to reduce harmonic distortion. A line reactor is an inductor that is placed in series with the input power supplied to the VFD. It helps to smooth out the current waveform and reduce the amount of harmonics that are generated. A DC choke is an inductor that is placed in the DC link of the VFD. It helps to smooth out the DC voltage and reduce the amount of harmonics that are generated. Harmonic filters are designed to block specific harmonic frequencies. They are typically installed at the output of the VFD or at the service entrance of the building. Upgrading the transformer can also help to mitigate harmonic issues. A transformer with a higher kVA rating will be able to handle the additional harmonic currents without overheating or experiencing other problems. Isolating the well power supply from the power supply to the adjacent homes is the most effective way to prevent harmonics from flowing into the homes. This can be done by installing a separate transformer for the well pump motor. The location is northeast approximately 9.6 miles up 5.9 degrees from Winged Horses. When dealing with potential harmonic issues related to VFD and shared electrical systems, a comprehensive approach is necessary. This involves understanding the nature of harmonics, their potential effects, and the various mitigation techniques available. Harmonics are essentially distortions of the sinusoidal waveform of alternating current, AC voltage and current. These distortions occur at frequencies that are integer multiples of the fundamental frequency, which is typically 60 Hz in the United States. VFDs, due to their switching nature, are a common source of harmonics. The rapid switching of semiconductors, such as insulated gate bipolar transistors, IGBTs, within the VFD to control the motor speed generates these harmonic currents. These currents can then propagate through the electrical system, affecting other connected equipment. The effects of harmonics can range from minor inconveniences to significant equipment damage. As mentioned earlier, harmonics can cause nuisance tripping of circuit breakers, leading to unexpected power outages. They can also cause flickering or dimming of lights, which can be annoying and potentially reduce the lifespan of lighting fixtures. Furthermore, harmonics can damage sensitive electronic equipment, such as computers, programmable logic controllers, PLCs, and other control systems. This damage can occur due to overheating, insulation breakdown, and other stress-related failures. In the context of an open Y-open delta transformer configuration, the potential for harmonic issues is heightened. This transformer configuration lacks a true neutral point, which can lead to the circulation of harmonic currents, particularly the third harmonic and its multiples. These harmonic currents can overload the transformer, causing overheating and reduced lifespan. The mitigation of harmonics requires a multifaceted approach, starting with a thorough assessment of the system. This assessment should include a harmonic analysis to measure the existing harmonic levels and predict the impact of the VFD installation. An experienced electrical engineer can perform this analysis using specialized equipment and software. Based on the harmonic analysis, appropriate mitigation measures can be selected. These measures can include the following. Firstly, selecting a VFD with low total harmonic distortion, THD. Modern VFD often incorporate advanced control techniques and filtering to minimize harmonic generation. When specifying a VFD, it is crucial to request a THD rating that meets the requirements of the application. Secondly, installing line reactors. Line reactors are inductive devices that are placed in series with the input power supply to the VFD. They help to smooth out the current waveform and reduce the amount of harmonics that are generated. Line reactors are relatively inexpensive and easy to install, making them a popular choice for harmonic mitigation. Thirdly, using harmonic filters. Harmonic filters are designed to block specific harmonic frequencies. They are typically installed at the output of the VFD or at the service entrance of the building. Harmonic filters can be either passive or active. Passive filters consist of capacitors and inductors tuned to specific harmonic frequencies. Active filters use electronic components to actively cancel out harmonic currents. Fourthly, upgrading the transformer. If the existing transformer is not rated for harmonic currents, it may need to be replaced with a transformer with a high kilovolt ampere kVAR rating and improved harmonic performance. Transformers designed to handle harmonic currents are often referred to as K-rated transformers. Fifthly, isolating the well power supply from the power supply to the adjacent homes. This can be achieved by installing a separate transformer for the well pump motor. This transformer should be sized to handle the load of the well pump motor and any associated equipment. By isolating the well power supply, the harmonics generated by the VFD will not propagate to the adjacent homes. In addition to these mitigation measures, it is also important to consider the grounding system. A properly designed grounding system can help to minimize the impact of harmonics on sensitive equipment. The grounding system should be designed to provide a low impedance path for harmonic currents to flow back to the source. This can be achieved by using a dedicated grounding conductor and ensuring that all equipment is properly bonded to the grounding system. Furthermore, regular monitoring of harmonic levels is recommended to ensure that the mitigation measures are effective. This can be done using a harmonic analyzer. If harmonic levels are found to be excessive, additional mitigation measures may be necessary. The selection of appropriate mitigation measures will depend on several factors, including the severity of the harmonic distortion, the sensitivity of the connected equipment, and the cost of the mitigation measures. An experienced electrical engineer can provide guidance in the selection of the most appropriate mitigation measures for a given application. In summary, the installation of a VFD on a shared well system can potentially cause harmonic issues that affect adjacent homes. To mitigate these issues, a comprehensive approach is necessary, including a harmonic analysis, the selection of appropriate mitigation measures, and regular monitoring of harmonic levels. Consulting with an experienced electrical engineer is highly recommended to ensure that the mitigation measures are effective and that the electrical system is protected from the harmful effects of harmonics. It is essential to remember that harmonic distortion is a complex phenomenon that requires careful consideration. Ignoring harmonic issues can lead to equipment damage, power outages, and other problems. By taking a proactive approach to harmonic mitigation, the reliability and efficiency of the electrical system can be significantly improved. When assessing the potential impact of VFD harmonics on adjacent homes sharing a transformer, several key factors need detailed consideration. These factors include the VFD specifications, the transformer's characteristics, the wiring and grounding infrastructure, and the sensitivity of the equipment in the neighboring homes. Firstly, the VFD specifications are crucial. The total harmonic distortion (THD) rating of the VFD is a primary indicator of its potential to generate harmonics. VFD with lower THD ratings are generally preferred for applications where harmonic mitigation is a concern. It is also important to consider the VFD input impedance and its ability to handle harmonic currents. Secondly, the transformer's characteristics play a significant role. The kilovolt-ampere (kVA) rating of the transformer determines its capacity to handle the load, including harmonic currents. The transformer's impedance also affects the propagation of harmonics. A higher impedance transformer can help to reduce the flow of harmonic currents, but it can also lead to voltage drops. As previously mentioned, the transformer's configuration, such as open Y-open delta, can exacerbate harmonic issues. Thirdly, the wiring and grounding infrastructure are critical for mitigating harmonic problems. Proper grounding is essential for providing a low impedance path for harmonic currents to flow back to the source. This can help to reduce the voltage distortion caused by harmonics. The wiring should be adequately sized to handle the increased current caused by harmonics. Fourthly, the sensitivity of the equipment in the neighboring homes is an important consideration. Some equipment, such as computers and other electronic devices, is more sensitive to harmonic distortion than others. It is important to identify any sensitive equipment in the neighboring homes and take steps to protect it from harmonic interference. In addition to these factors, it is also important to consider the overall electrical system configuration. The presence of other harmonic generating devices, such as uninterruptible power supplies, UPSs, and electronic ballasts, can contribute to the overall harmonic distortion in the system. To accurately assess the potential impact of VFD harmonics, a detailed harmonic analysis should be performed. This analysis should include measurements of the existing harmonic levels in the system and simulations to predict the impact of the VFD installation. The analysis should also consider the different operating conditions of the VFD, such as varying motor speeds and loads. Based on the results of the harmonic analysis, appropriate mitigation measures can be selected. These measures may include a combination of the techniques discussed earlier, such as using a VFD with low THD, installing line reactors or harmonic filters, upgrading the transformer, and isolating the well power supply. It is important to note that harmonic mitigation is not a one-size-fits-all solution. The best approach will depend on the specific characteristics of the electrical system and the sensitivity of the connected equipment. Therefore, it is essential to consult with an experienced electrical engineer who can perform a thorough assessment and recommend the most effective mitigation strategy. Furthermore, it is important to consider the long-term implications of harmonic distortion. Harmonic distortion can lead to increased energy losses, reduced equipment lifespan, and other problems. By taking steps to mitigate harmonics, the overall efficiency and reliability of the electrical system can be improved. In conclusion, addressing potential harmonic issues related to VFD and shared transformers requires a comprehensive and systematic approach. This involves considering the VFD specifications, the transformer characteristics, the wiring and grounding infrastructure, the sensitivity of the equipment, and the overall electrical system configuration. A detailed harmonic analysis should be performed to accurately assess the potential impact of VFD harmonics. Based on the results of the analysis, appropriate mitigation measures can be selected and implemented. Consulting with an experienced electrical engineer is essential for ensuring that the mitigation measures are effective and that the electrical system is protected from the harmful effects of harmonics. By taking these steps, the reliability, efficiency, and lifespan of the electrical system can be significantly improved. Finally, let's consider some specific scenarios and examples related to VFD harmonics and shared transformers. Firstly, imagine a situation where a VFD is installed to control a well pump motor in a rural area. The well pump is used to supply water to several homes in the area, all of which are connected to the same transformer. If the VFD generates significant harmonic distortion, it can cause problems for the residents of the homes. For example, the harmonic distortion can interfere with the operation of their electronic devices, causing them to malfunction or fail. It can also cause the lights in their homes to flicker or dim, which can be annoying and potentially reduce the lifespan of the lighting fixtures. In this scenario, it is important to take steps to mitigate the harmonic distortion generated by the VFD. This may involve using a VFD with low THD, installing line reactors or harmonic filters, or upgrading the transformer. Secondly, consider a situation where a VFD is installed in a commercial building to control an HVAC system. The HVAC system is used to provide heating and cooling to the building, which is occupied by several businesses. If the VFD generates significant harmonic distortion, it can cause problems for the businesses in the building. For example, the harmonic distortion can interfere with the operation of their computers and other electronic equipment, causing them to malfunction or fail. It can also cause the lighting in their offices to flicker or dim, which can reduce productivity and create an uncomfortable work environment. In this scenario, it is important to take steps to mitigate the harmonic distortion generated by the VFD. This may involve using a VFD with low THD, installing line reactors or harmonic filters, or upgrading the electrical system. Thirdly, let's think about the situation where a VFD is installed in a manufacturing plant to control a motor that drives a conveyor belt. The conveyor belt is used to transport materials throughout the plant. If the VFD generates significant harmonic distortion, it can cause problems for the plant's electrical system. For example, the harmonic distortion can cause the plant circuit breakers to trip, which can disrupt production. It can also cause the plant's transformers to overheat, which can reduce their lifespan and potentially lead to a fire. In this scenario, it is essential to take steps to mitigate the harmonic distortion generated by the VFD. This may involve using a VFD with low THD, installing line reactors or harmonic filters, or upgrading the plant's electrical system. These examples illustrate the importance of considering harmonic distortion when installing VFD in various applications. By taking steps to mitigate harmonics, potential problems can be avoided and the reliability, efficiency, and safety of electrical systems can be improved. Remember, consulting with an experienced electrical engineer is crucial for assessing the potential impact of VFD harmonics and recommending the most effective mitigation strategy. The engineer can perform a detailed harmonic analysis, evaluate the electrical system, and consider the specific characteristics of the application to develop a customized solution that meets the needs of the customer.